Okay, and raise your hands again if it is way too hot where you are. Okay, right. We got a lot of hands raised, okay. I'll make sure everyone's super on their toes, you know, we can communicate back and forth. It's way too hot where I am as well, so if you see me getting redder and redder, that's what's happening. Okay, well, let's get started with the second topic session. Basically, what we're going to talk about this time is Module 3, and we're going to go over some of the time complexity as well. If you have questions, go ahead and just drop them in the chat at any time. If you're confused about something, go ahead and just drop it there, and then I'll pause periodically to answer questions and dig into anything that y'all want me to dig into. Especially since we don't have a huge number of people, you know, your questions, I can probably get through all of them. So just go ahead and ask, it helps. Yeah. All right, so what we're talking about today in this section, we're really going to focus more on the review and the evaluate phases of the umpire method. In future modules, we're still going to have all those understand, match, plan videos for the first few practice problems. And then as we move along, we're going to be focusing a little bit more on the review and evaluate phases in these guided topic sessions so we can get into the nitty-gritty details. We're going to talk about kind of walking through stuff, a little bit of debugging, and then we're going to analyze space and time complexity and talk about in Python, when you see certain Python syntax, what kind of space and time complexity are you seeing there? We're going to talk about a couple of different Python tools as well. We're going to go over lists very briefly. Just going to show you append, pop, and insert. And then we're going to talk a little bit about what sets are and how they're distinct from lists. I'm going to show you list and set comprehensions, just so that when you're looking up code online and you see other examples, you can read it a little easier. If you've never seen list or set comprehensions, they can be kind of like really jarring. So I just want to show them to everyone. I'm also going to show you a little bit of Bitwise Operations. I'm not going to get super deep into it, but this week we'll dig into it in a much later module. But I'm just going to talk a little bit about what they are and what you're seeing when you see these operators in Python. Okay, so any questions so far? Anything that anyone wants to bring up or talk about before, or any questions you might have about the course or what's going on with that? Let's for a moment. So I hope everyone is staying hydrated, and we may take some biology breaks during this course because everyone better stay hydrated. It's super hot out there. Okay, so let's talk a little bit about interviews. We're about to go over the review and evaluate phases. And if you recall from the umpire method, these phases are at the end. So I kind of want to talk a little bit about the different types of interviews that you might run into, and which ones that you really need to focus on, like the review and evaluate and the efficiency of your solution versus just solving a problem. So there's three types of interviews that I've really seen a lot of people go through, from like the most junior type of interview to the least junior type of interview. So the very first interview is, can you write code, right? A lot of times for like an internship or junior software engineering position, what you're really interviewing for is, can this person take requirements and turn them into code? And then they kind of assume that someone more senior than you is going to be looking at your code, reviewing it, and then telling you where you might be able to optimize things. Second type is, can you optimize? And in this interview, it's going to be very different. In the first interview, you'll write code maybe in an IDE, maybe on the whiteboard, but usually they're not doing that so much anymore, where you have to like remember all the syntax and details and you have to write it down. But can you optimize? That second type of interview is really more about discussing how the problem is solved and then your approach to the problem. you'll be writing pseudocode, and so they're looking to see, do you know the tricks? Do you know the little things for this problem or problems like this? So these can you optimize they're a little bit testing your ability to plan and then evaluate. They're less focused on like the code or the implementation. And then there's can you design? And so these are the most like advanced or high level interviews. And what they want you to do in these interviews is kind of talk about 3 or 4 abstract implementations for some system or some problem and discuss the drawbacks of each, right? So you can kind of see how the interview shifts from the understand, match, plan phase all the way through to the like really optimizing phase. So for you, for going into your very first roles or your very first internships, this is kind of what I think like a lot of interviewer expectations are. But the very first expectation that an interviewer has is that you connect with them as a person and you understand their goals. So just ask the interviewer, what are you actually looking for me to show you in this interview? And they'll give you kind of a high level, and they'll at least help you to categorize the interview into one of these 3. The approach is different because, for each one of these, because it focuses on several different things. If you're just trying to get to a code that works, it's really best not to worry about what the most optimal path is first. But if what they're wanting you to do is design and match across a lot of examples, then you don't want to really just show up with the brute force solution first. So you can ask an interviewer, what are you actually testing for? Do you want me to show you code? Do you want me to show you a couple of solutions? Or are you really wanting to talk about things high level? Just ask as your first question. The second thing that they care about that you see is understanding the problem and then wrestling with the problem. When I say wrestle, what I mean is your willingness to like jump in and try to figure it out, right? So they want to see you take steps to, break the problem down into smaller problems instead of just going, okay, I'm really not sure what to do here. I'm just not sure what to do, and freezing up and putting your shoulders up like this. Then that you can discuss the problem, ask questions about the problem, create plans for the problem, follow the Empire method, solve it, test it, evaluate the solution, determine and understand the improvements for the solution. Sometimes an interviewer will lead you to improvements and say, maybe we could use a set here. Maybe we could do this or that. And if you need to show that you understand those improvements and that you can implement and test those improvements. And at the very end, that's what they really care about, is at the very end that your solution is the most efficient solution. But let me stress, for sure, definitely the very first thing you should do is ask about the interview itself. Okay, so now that you know, we're not expecting your first solution to be the most efficient solution, and that is not the best way to get to the problem. I want to talk a little bit. I'm sorry, I just want to say, like, functioning solutions are better than unfinished solutions. Anytime you're in an interview, they want to see you get to the end so that they can talk to you about your code and they can see how you respond to feedback and how you implement feedback. If you never get to a working solution, they can't do that. Working solutions are better than buggy solutions. So, if you're hand waving past the details, they're not going to be able to really evaluate whether or not your solution works properly or that you can get all the way there. But really, it's about getting to a quickly completed solution so that you can make those iterative changes. That's what interviewers want to see, is get to a point where then we can talk about the problem like two people who have wrestled with the problem before. But optimized solutions are better than naive solutions, and we do want to show you all these details about how to, optimize solutions and give you enough of a plan base to match, give you enough of a match base to match off of in later interviews. So, speed in an interview really does matter, and your ability to get to these solutions quickly will come into play. But you know, you really want to focus on having something to optimize before you do this. Okay, so transition, we're going to get into runtime complexity. Now, I'm not going to throw a bunch of math equations at you. A lot of times we look at like this big O thing, and if you haven't been through this subject matter before, it kind of looks really complicated. But really all we're doing is describing how fast the number of steps that our program has to take will rise based on the size of the input. If the input's bigger, does the algorithm take twice as long, an exponential amount of time longer? And so you can see in this diagram that I got from bigocheatsheet.com, which is one of my favorites, it kind of explains, like, you can see all these different lines, and you can kind of see it's been rated horrible, bad, fair, good, excellent. And down here, if you're colorblind, you know, these are the excellent ones. The execution time doesn't grow very quickly in relation to the input. But these over here, a lot of algorithms end up over here, or a lot of solutions end up over here, where, you know, we're checking n against n, or we're checking n against n to the, you know, to the power of itself, or n to the power of n, you know. So those are the really bad solutions, and I just want to show you kind of a couple of different ways to recognize what your solution's runtime complexity is. So there's a couple of questions that you can ask yourself, and a couple of just simple things that you can do to look at your problems that you have been working on and determine what is the runtime complexity. So the very first thing, identify the input and which dimensions account for size. If you think about, if you've looked at the Pascal's triangle problem, the number of rows accounts for the size, right? Not the length of the arrays, it's the number of rows that's the main dimension. Whereas if you're thinking about the single number problem, it's the size of the input list. In the counting primes problem, it's what number are we counting up to? And the dimension that accounts for size is the size of the number, not the number of numbers. So is it an input value that is a number that kind of accounts for the size, or is it the literal input, like the length of a list or the length of two lists that you're comparing? So that's you've got to identify n in order to figure out how n has a relationship to the solution. Okay, and then the next question you want to ask is, how many times do I interact with every element of the input? What we're talking about here is, like, if you've got to check every number under n, how many times do you have to do something with that number? And does it change based on n? The best way to do this is first count the loops. You've got loops in your code. If you've got a loop inside of another loop, take a look at what those loops are operating on. Are they operating on a fixed amount? Like, are they always going from 1 to 3? Or are they operating on n times itself? Or are they operating on, you know, the array next to the other array? I'll show you some examples in a few minutes about what these actually look like. And then I'm gonna drop them in Python tutor, and so, or sorry, I'm gonna drop them in the chat so that you can take a look yourself. The next thing that you want to do, and I'll be talking about this shortly, is you want to count the, like, hidden loops. In Python, whenever there's a couple of different data structure access operations and a couple of other, like, lines of code that seem like they're one operation, but they're really looping over something just kind of in one line. And so we're going to identify those so that you don't get, like, secret complexity that you don't realize you have. And then you want to check your data structure access. Accessing a hash table versus accessing an array versus accessing, you know, a deeply nested dictionary with dictionaries inside of it versus, you know, looping over every number up to n. Like, all these different data structures, they have different complexities to interact with. And as we kind of break, like in the further modules, like way in advance, there's other more complex data structures like linked lists that have more complex runtime requirements. The next thing to check is how many times do I interact with the data that is dependent on the input. So for instance, if you're doing something like filtering the input list for duplicates and then doing something with that input list that has duplicates in it, you're still operating on n. It's a subset of n, and maybe it's a predictable subset of n, but you're still operating on something there. And so as the input grows, that secondary data that you've maybe created in your function is part of that. And you know, it's maybe reduced, but it's still, as the input grows, will grow in relation to the input. So checks over filtered input data, how large and how, you know, what's the maximum size if it's guessable, that can factor into your input. The other thing is recalculating. And you'll see this a lot in anytime you try to use recursion in an interview, especially if you're going to recalculate anything with that recursion, you may be adding a lot of steps that you don't really realize that you're adding. For instance, if you're going to, you know, calculate all the prime numbers under a number, check one number with that, and then be done with that calculation, and then move on to the next number and have to recalculate it. I see a lot of solutions like this, and these greatly increase your runtime complexity. And so there's some approaches that we can take. You know, if you're dynamically calculating data, that you can sort of save it and keep it so that you don't have to redo it. This is obviously at the cost of space, and so there's always a trade-off there. And then, you know, that's sort of another thing is as you use more space, like one of these, you know, filtered input data, you know, data structures where you take input data and do something with it and you add it to that thing. As that grows and as your space grows, like what does that do to complexity? Are we checking more and more often, right? Or are we checking more and more elements? So these are sort of the steps to determine runtime complexity. And what I'm going to do is kind of show you a few examples here. Pull these up. And if you have any questions, drop them in the channel while I'm pulling this up. Okay. So just quickly, we're going to look at this. And I'm going to use it to also kind of talk a little bit about lists. All right. There we go. All right. Can everyone see this right here? All right. So if you've heard the term array or list before in Python, hold on, sorry, let me pull this up. There. Just gotta get it over here so I can see it. Okay. There we go. Okay, so if you've seen a list before or an array in any other programming language, you'll recognize that Python lists are basically arrays. They're a little bit more flexible than maybe arrays you've seen in the past. You can put kind of whatever you want in them, so I could kind of have like a hello string here, and that's still fine. I'll even run this, and you can kind of see that it's definitely still fine. And this is the syntax here to access an array or list in Python. Anytime you're Googling arrays or lists in Python, use the term list and it'll help you get the right result. So what we're doing in this example here is we've got a function, and all it really does is print the first item in an array. In this next function, we are looping over an array. And so this is a common pattern that you'll see anytime that you're interacting with an array. And what you'll see is for I in the range We're familiar with the range function of the length of the input array. And so that'll get us all of the numbers from 0 to basically right before the size of the array, right? And so that'll be the last index. And so you can do this for loop to get every element in an array by its position. If you look at this previous one, this is accessing that very first element. So that's always going to be 1. No matter what the array has in it, it's always going to be this very first element when you type 0 in there. But in this example, we have an iterator variable, and so we're using that iterator variable to access every element in the array. And then in this example, you can see that we've used this same pattern 2 times in a row. This for loop is inside of this other for loop. So this for loop runs over the whole length of the array once for every element in the array. So so you'll see every number printed next to every other number. Now, in Python, you'll have to use another iterator variable name if you're going to do 2 for loops like this. So there's I and J here. So that's kind of like a pattern that you'll see a bunch of times. I just want you to be able to kind of read this. Now let's talk about the runtime complexity of each of these. One of the best ways we can do that is by just watching it happen in Python Tutor. So if you look at the number of operations that this function does, you can see that no matter how long the array is that we pass into the function, it will always only take 2 steps really to execute. It never has to go any further than the very first one. And so this is an operation that we would say is constant. It doesn't grow with the size of the input. So no matter that A1 or A2 is twice as long as A1, or that A3 is twice as long as A2, we always just had 2 operations. In this example, it's different, right? The number of operations that this function executes are larger depending on the different inputs, right? So we're going to allocate all 3 of those lists. And you can see in Python Tutor up here, when you see a list, this top number is the index and this bottom number is the actual value. So we'll go ahead and call it this first time. And so this print all items is being passed in this array. And you'll note that in Python, we're not creating any like new array just to kind of exist in the function. Data structures like this are passed in by reference. And so this, where it says array, is now pointed to the same variable as A1. So we didn't create a new thing. So, and then, all right, so there's 3 elements in this array. Let's count the number of execution steps. There's 1, 2, 3, 4, 5, 6, 7, 8. All right, 8. Now let's look at the number that happens when we pass in A2. You can kind of see that here. A2 array is now pointing at A2. We pass this in here, and oh, let me count. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so 14. So it grew, we went from 8 to 14, right? And that's kind of only because we're counting this like all items print statement, right? The main part of the loop, or the main part of the function that changes the number of steps is this loop, because it's looping over the size of the input array. To go on to this next example, basically what we're doing is we're passing in the same 3 arrays, up to 3, up to 6, and up to 12, right? And then you can kind of see that these steps down here are huge, way larger than these other two, right? Like the largest number over here was 61. Over here we were at 19. So Python Tutor can kind of, just by telling you the number of steps here, give you an idea of how quickly it grows. If I were to click on this, you'll note that in Python Tutor here, can I zoom? Press the command. I can't zoom in. Oh, no. Okay, can't zoom in. But basically, it's down here. You can kind of see, if you look at these little red lines underneath in Python Tutor, you can kind of see at what step is this line called. And you can see that it grows, right? It goes from here to here to here, and then it more than doubles over here, right? So this huge jump between these two and this one shows you that, you know, the last time that this is called, and I'll just go ahead and fast forward, and it'll kind of like run it for me and then jump to the next one. In order for me to run print all pairs on this A3 array with 12 numbers on it, it goes from step 124 to 439. So it's, you know, about 300 or so steps. It's pretty huge. And so this is O of n times n, right? That's what we would call this operation, because n is the length of the array in this situation. This loop puts us at O of n, but then this second loop means that we have to multiply n by n to get the number of steps. So the number of times this line will execute depends on the length of this, and the number of times that this line will execute depends on the length of this times the length of this. Okay. Let's pause, just think about this for a second. If you have any questions, let me know. I made this little Google Sheets thing, and it's linked in your course portal. Basically what it allows you to do is just kind of plot the execution steps that maybe you got from Python Tutor, just from counting. And I linked it so that you could kind of use it and make your own. But you can kind of see just these three functions: print first, our execution steps were 2 every time. So the line is flat. With print all, it went up 8, 14, 26. So the line doesn't grow very fast, but it grows a lot faster than, you know, being flat, right? But print pairs grows and it just like takes off super fast. You know, we doubled twice, and we've gone like way more than double. You know, 89 steps to 316 steps. Like, you know, it's at least triple, right? It's more than triple. So it's growing faster than a linear relationship. If the number of steps always increases in a predictable way, like the same number, you know, like if you have like your input of n and you do something 3 times to each element, right? Then you're really just linear, because that's how fast the number of steps is growing. It's just a direct linear relationship. It's not 1 for 1, but it's linear. But in this one, it's related to n times n, right? And so that's super linear. It's not quite. It's O of n. Let's see, not squared. It's just O of n times n. I mean, I don't think that there's like a term for it. So that's kind of the difference between these 3 operations. And when you're working with lists or you know, arrays in any language, these hold pretty true. And so this is pretty similar to this, like, determining runtime complexity. Count the loops, right? That tells us how do we find So now I want to talk about hidden loops, but for that we need another example. And I think that the best way to do that example would be to probably talk a little bit about there's a problem in module 3 that is, you know, the list term, and it's also here in LeetCode, and it's called single number. There's only the one single number in this problem, so let's look at it together. Anyone, before we start, have any questions so far about this whole thing? Okay, so given a non-empty array of integers, every element appears twice except for one. Find that single one. So I'm gonna move a little quickly through this solution. So if you have any questions, please raise your hand and or type it in Zoom. If I'm going too fast. But yeah, let's kind of get started. Now, I'm not gonna code this here because, for instance, you know, there's not really anything, there's no playground available like it says. All I can really do is submit a solution. So I don't really want to develop it. So what I want to do instead is I'm just going to take this input here and I'm going to move over to Python tutor. Let's see what I have. So there we go. So I'm going to go over to Python tutor and I'm basically just going to write down the two examples and what their output should be. And then we're going to solve this step by step together. So first of all, let's look at the prompt and ask our, understand questions. What's the input? Well, it's a non-empty array of integers. So they don't want us to worry about corner cases like the empty set or wrong inputs, right? It's going to be integers. So we know, integers, right? Every element appears twice except for one. Okay, so I actually got this interview question once at Solar City, and I got to the answer that I'm about to show you, but I didn't get to the next two levels up, right? And this kind of explains what it was that they were really looking for in this interview. Your algorithm should have a linear runtime complexity. So as this non-empty array of integers is input and it's larger and larger, the number of operations that we can do on that has to grow only in relation to the input. If we have a double loop in there, that's not going to be linear. So, okay. And then there's this second question. Could you implement it without using any extra memory? Now, anytime you see without any extra memory, don't assume that that means I can't use an iterator variable in a for loop, or one variable to restore, store the return value in. A lot of times that's not what interviewers mean, but ask, clarify. In this particular example, there's maybe two extra variables, but there's not a lot of extra memory. There's not extra memory that grows in relation to the input, right? We don't create a new data structure to hold other information. So yeah, there's a couple of different solutions to this, but again, we want to see you get to one solution and then optimize. Okay, so let's go through the process here and try to figure it out manually. Let's see. All right. So if I am a human being trying to find that one is the answer here, what I would do is I'd go over each one. I'd say, okay, I see a 2, so I'm just going to write down that I saw 2. I'm going to go see the next 2. I know I'm not going to encounter a third 2, so I'm just going to delete the 2 that I found, and then I'm going to write down that I saw 1. Okay, I've reached the end. 1's the only number I have left, so that must be the singleton. All right, cool. That was a process. Let's make sure that it it works again. So all right, I saw a 4, and then I saw a 1, and then I saw a 2, and then okay, I saw a 1, but I have 1. I'll get rid of that, and then I saw a 2. Okay, I have a 2, so I'll get rid of that. All right, the only number I didn't delete was 4. So that kind of filter, that works, I think. So let me sort of write that process down. Let's see. For every element in the input list, if I have seen this element before, what I want to do is remove it from the list of elements I have seen before. Otherwise, add it to the list of elements I have seen before. Okay, that's a pretty good description, I think, of what I tried to do there. So I'm going to just define my function, def, and what do I want to call this? Single numbers. Okay, and then we'll have the input list, so integers. And then, okay, I've got this Python sort of pseudocode here. Got my for loop. I'm going to create a variable to just hold on to the array that I might be, I'm going to create a variable to hold on to the list of numbers I have seen before. I like to do these super verbose variable names. And then for every element in the input list, right, let's the input list. And then we could call this element integers. Got our colon there. Boom, we got Python code. Okay, so now we know this is an else, so I'll just translate that otherwise to else. And now we have to ask ourselves, if I have seen this element before, how do I get that? Well, we can say element in integers. And what this does is it checks every element in integers to see if it is an element or is the same as this element. And if so, this whole statement returns true. Otherwise, it returns false. Okay, so now numbers I have seen before. I'm going to remove it from the list of elements I have seen before. I'm going to call the dot remove function or method on this list. I'm going to pass an element. And what that does is basically searches this list for the element, and then it removes it once it finds it. Otherwise, it doesn't do anything. It changes this list. That's another thing that you should keep in mind, that this doesn't return a new list with this element removed. It modifies this original list. Otherwise, I need to add it to the list of elements I've seen before, so I'll just do that, dot append element. At the end, return the last element that I have, so numbers I've seen before. And then how do I remove something from a list that I don't know what it is? Well, I'll just use pop. And what pop does, if you don't pass it an argument, is it just takes the element off the end of the list and returns that element. It is destructive, so it changes how the list works. It changes what's in the list, and it returns that element. So, okay, so now that I have kind of written up this example, what we're going to do is we're going to evaluate it. And so I'm going to ask you all to tell me what you think is a loop and what isn't. Because we talked kind of a little bit about hidden loops. How do we find the hidden loops, right? So let's visualize this execution. Let's make sure that this works and that I'm not breaking everything. And oh, okay, cool. X is not in list. Oh, I need to edit that. So if element in integers, wait. Oh, if element in numbers I've seen before. There we go. Anyway, yeah, way more steps now, so we're not probably going to throw an error, at least on that one. Okay, so I can kind of walk through this and see elements 2. I'm going to throw it into the numbers I've seen before. And then, oh, it looks like I've seen it before, so I'm going to pull it out. And then add 1. And now I'm done, so I'll pop that element out. You can see numbers I have seen before that pop statement contained this single number. And so now it doesn't contain anything. And then what we return is that element. Okay, so let's make sure that it works for another example. So we've added 4 to the list. Now we're going to add 1, now 2. Oh, no, wait, let's get rid of 1. And okay, let's get rid of 2. And now we're returning 4. So I know that was super lightning fast, but let's just take a moment to look at this code together. And let's try to determine, you know, where are all the operations here that grow with respect to the input value. Any operation that is dependent on the size of n, how does it grow? So I want you to, there are 1, 2, 3, 3 lines in this that change the number of operations. And I'd love to see you all put them in the Zoom chat. Don't look at the what people are saying in Zoom chat. Just look at the code and then type in the chat, kind of without looking. What line numbers cause our execution times to grow? Okay, so we've got several answers in here. If you're still looking, I'll give you another 30 seconds to try to just make a guess. You know, if you're not sure, make a guess. Okay, so the correct answer, Eli Wald and Victor Rodriguez, y'all got the correct answers. The answers are 3, 4, and 5. All affect our runtime complexity based on the input size of our input. So 4 element in integers, that's based on the input size. So pretty much everybody got 3. Now let's look at line 4. If element in numbers I have seen before. So you remember how I talked about filtered input data and how since filtered input data grows in relation to the input size, this line appears like it's one operation, but really we're taking element and we're individually comparing it with every single element in numbers I have seen before. So we're going element by element, right? And this list, you know, in these two examples, it's real tiny. It never gets to be super big. But let's imagine a list with, you know, 1,000,000 integers in it and only one. The numbers I had seen before list would get to be really huge. Even if you were quickly filtering them, you know, that size would start to get really large and can really affect the runtime complexity. The other one is 5. That might be a surprise, but what remove element is doing is not going to that index and just taking that out. What it's doing is checking to see every element in the array or list or whatever we're calling it. And then it's finding, as soon as one of them matches by comparison, by like direct comparison, then it will remove that. So, you know, it might happen early in the list or it might happen at the very end of the list. You don't know where everything is in the list. And so these 3 lines affect our runtime complexity. But they look like one line, right? They look like we're just doing one step there. So that's kind of one of those things that can get a little confusing. So just kind of make sure that you understand like these lines of code. Am I looping secretly without realizing it? This looks like an if statement. It says if right there. That's one line, right? But it's not. It's actually a loop. So yeah. Okay, cool. So now that we've kind of looked at our code and we've identified that these 3 lines are really what are kind of, you know, making it difficult for us, what we can do is a couple of different things. There's one thing that we can really simply do that will remove some of the burden from just this implementation by itself. And that is to use what's called a set. And so a set, and I can kind of do this here to create a set of nothing. Basically, if so there's this idea called a set. And what a set is, it's like a list, but there are no duplicates. Every individual element in a set is unique. And a set it's similar to a hash table, but rather than having keys and values, it just has keys. And so what you do is you can check for the membership of an element within a set. You can check to see if a thing is in a set, and you can do it in constant time rather than looping over the entire array to find it. So rather than append, we use add, and that's kind of the main thing. And so let's see, I can't remember if it's pop or let's see, it's pop. We'll see. We'll look it up in a minute if this doesn't. Okay, so by changing this to be a set, we can watch our thing run and it still runs, and we add things to it, and you see how it says set, and it looks a little different. There's like there's a box around it, and you can kind of see it get removed. And so the thing about this line 4, which was affecting our runtime complexity by a whole lot, this is optimized with sets to only be constant time. So you can say if element in numbers I've seen before, and that's just like a O of 1 operation. It's constant. Adding things to a set is constant, and removing things from a set is constant. So we can see this kind of go through and add things to this much larger set. And you can see there's like almost no dividing line between them. And there's no, unlike a list, there's no index, right? This isn't, the 1 isn't at index 0 and the 2 isn't at index 1, right? All we can really do is ask this set, is there a 1? Is there a 2? We can loop over a set and it will, and then like the things inside the set will not come out in like a stable order that we can guarantee. So if you need things to be ordered, you still have to put them in a list. But with a set, you know, there's no duplicates, right? So it's much more efficient to use a set for a lot of different things. Okay, so you can kind of watch this go through, and like when the removal happens, that happens at all. You can't see this in Python 2. You notice that you didn't see if element in numbers I've seen before. When it was a list, you didn't see that iteration happen. But it does. That's how it works in Python. So it's something to keep in mind if you're going to use Python. Okay, so that's the first implementation of this example. And what we did is we looked at our code and we identified places where, like this, oh, also this removal statement, line 5, which was also impacting our runtime complexity, is also now O of 1. So these set addition and removal operations are O of 1 operations. We can't really reduce going through integers because we have to go through integers. So what we've achieved now is linear runtime complexity, because there's no extra operations on the input that change the runtime complexity. So we've gotten to a linear place. Now, the hard part is really going to be in translating between our linear solution and our no extra memory solution. Because a set, we're still using extra memory. We're creating another data structure and taking data and putting it through, right? So our space complexity is, you know, it's O of n times, or n plus n, which is, you know, it's really just n. It's linear. The way that, you know, space grows as this function gets bigger is linear, but it's not constant, right? And we can do this constantly in constant time, but you have to know some tricks for it. So I just want to ask, has anyone ever seen a problem like this? And do you know any of the like math tricks that we can do here? The first is math, right? First thing that we can do. Just raise your hand if you have seen this before. And you know, like a math trick. Okay. That is fine. Totally cool. So, so let's kind of talk about what's going on here. Essentially, you've got, okay, so you've got this sequence of integers, right? And there's this trick with math, right? So essentially, if you have these pairs, and what you want to do is kind of like cancel them out, what you need to do is essentially, let's see, I had to look this up because what I had to do was remember all the tricks about sequences of integers. And so this is something that you can learn and you can identify in an interview, but it's not something that they usually want you to just like know from first principles, or just know because you know math, right? This is one of those like math tricks that you can use. So the reason this works is, so if you think about what is, let's see, the sum of, well, sum of the list. And if you think about, like, if you've ever used these functions in Python, sum, you can pass in an array. And I'm just going to say, you know, list is here. I'm going to add this list because it's big enough to kind of visually see what's going on. And so if you sum the current list, what I'm going to do is jump into live programming mode so you can kind of see these variables change, right? So if you look at the sum of this list, it's 10, right? Now that's 4 plus 1 plus 2 plus 1 plus 2. So if we also take a look at the sum of the set, right? What we can do is sum the set of the current list. And what that will do is it'll translate current list into a set of numbers. And so basically it'll like dedupe current list for you. So that's what this expression is. And then I've called this sum function around the set function. So what that does is it takes every number in the set, it iterates over the set. So that's what this operation is doing. This operation iterates over the whole current list to create the sum. And this operation iterates over the whole current list to create the set. And then this operation iterates over the whole current list to create the sum. So that's what we've done so far. So if you look at the sum of the set, you can see that it's 7. And if that gives you a hint as to what's going to happen, like cool, maybe you've been playing with like, you know, integer sequences for a lot. And if you're really into something like signal processing, you might want to get into like the behavior of integers and like what happens when you sum them. But if it's not obvious to you yet, basically if you multiply this by 2, you'll note that the sum of the set when multiplied by 2 is 14. And so if we just add all the numbers within the current list to together, we get a number. But then if we add the uniques together and then double it, it's kind of like creating this array but with no single number. So we've kind of recreated this but without the singleton really present. So they're all doubles. So now that we have these two numbers, it's just the ones that the sum of the doubled list minus the sum of the doubled list without the other double, which will give you the single individual number. So, you know, singleton is the sum of the set minus the sum of the list. Right? And so now you can see that the singleton is 4 here. So that's sort of a tricky mathy way to do it. And if you didn't get there, I mean, it looks like there's 3 lines. But again, what we're doing is we're actually iterating over the current list, you know, this list here, once, and then 2 times here. So we do it 3 times. Whereas up here, I think what we do is we go over it 1 time. So there are actually technically fewer operations here, but this still grows linearly with the size of the input because we have to do these operations. It appears more elegant and it doesn't, but it uses more memory because we have to create this set. Actually, it doesn't use more memory, sorry. It doesn't use more memory, it uses about the same amount of memory because we have to create this set and add members to it. We're using more like variables here, but it's a very elegant solution that'll get you there a lot, pretty fast. So now there's like this third solution, and you know, if you haven't dealt with a lot of bitwise operations, this solution can get really tricky. I'm going to take a break here for about 2 minutes just so that everybody who's drank 1.5 gallons of water, which is how much you need to drink, can use the restroom and stare at this code and go, what? For a minute. So let's just take like 2 minutes and kind of break, and then we'll come back. And then we'll go over the last, most efficient solution there is. Also, I'm here for questions, so if anybody's got questions, let me know. Okay. I'll answer his questions in a second. Oh. I'll just go ahead and generate this permanent link. So I dropped a permanent link in the Zoom group chat. Please don't share that with the Slack group yet, because some people are not, like, they're not here yet, and so we want them to like exercise, play with it before they get a chance, before they just get it spoiled. You know what I mean? So just you have that, and then I'll give you, I'll give it out at the end of the week to Slack. Okay, it's about 7:08, so we're gonna get back to it. And in order to do that, I'm going to jump into this solution. So, okay. So, one of the first things I want to talk about is not actually this this solution. It's about identifying when you want to use the inverse of a function to. Okay, so there's this thing that we do a lot actually in programming where we kind of have some data and then we do an operation on that data and then we reverse that operation and to get back the original data. And it's a pretty common thing, and there's a couple of different operations that do it. So like a a two-way hashing algorithm does that. Bitwise OR does that, but this also does that. This is an example of that. So I wanted to just kind of walk over. This is how we can swap two variables without using another variable, as long as they're numbers, right? So if you've ever tried to swap two variables before, like in Python, you can kind of do it by using like a tuple assignment, but that's cheating and you're creating more memory and that kind of stuff. You're really secretly creating another variable. So this is how we can do it with just these two variables. We're going to swap x and y. So x starts at 15 and y starts at 10. So what we're going to do is we're going to operate on x with y. We're going to change x by y. We're going to add x to y. And so what happens is that sort of like destroys X, right? X is now gone. But because we still have Y, and Y is what we use to operate on X, and addition can be reversed by subtraction, because all of those things are true about numbers that are positive, then these two operations work. And so kind of we've got Y, what we're doing is we're setting Y, but what we're doing is we have X, which is 25, and then minus Y, which will turn Y into what X was. So now let's watch that happen, okay? Y is now 15, so how do we get our 10 back? Well, if X is X minus Y, that's the original value of Y. That's how we got to Y, but with, you know, different numbers in different places. You can kind of see this happen here. Now Y is 15. And so you can see X started at 15, now it's 10, and Y started at 10, now it's 15. And that's because this is how you reverse those operations. And it's kind of the same dynamic as this other idea here. So I'm going to do the same exact thing, but I'm going to use a different operation. So this is, let's see, let me click on that. So if you look at this, what we're going to do is we're going to swap A and B using Bitwise XOR, XOR, which stands for exclusive OR. And what a bitwise operation does is it goes, it breaks the number, the integer value, down into its binary components. And then it goes number by number and compares each bit. And there's bitwise OR, bitwise AND, bitwise XOR, and then there's bit shifting, right? There's a lot of these tricks, but I'm just going to show you OR because it's kind of the same idea of reversible operation. So I've created these other variables so that you can see what the binary values of A and B are. They're not really part of this, they're just so that you can see it in Python. So if you look at A and B, 25 and 15, and then we have a binary A and a binary B. This is what A is in binary. That 0B just kind of tells Python, hey, treat this as binary. And then the rest of these are individual bits. If you look at them, 25 25 is larger, so it's got an extra place value. And so these get compared at the sort of end here. So this one gets compared with this one, this 0 with this one, this 0 with this one, this one with this one, and then you can kind of imagine that there's an extra 0 in front. And so this one will get compared with that invisible 0. Okay, so now let's look at what happens when we bitwise OR, which means exclusive, so one or the other, but not both. What happens? So we did the operation, and A became 22. Let's update our binary values just so that we can see what that looks like. So now binary A is the one that got operated on. So B kind of got like passed through A, right, and flipped all its bits. If there were two of the same, like two ones, that became a 0. If if there was a 1 and a 0, that became a 1. And if there were two zeros, then that became a 0. So you can see that A has become 1 because there was a 0, 0 because there's a 1 here, and so basically all of these will get flipped over. The two zeros are now 1s, and then the end that was a 1 is now a 0. So now let's look at what happens when you bitwise XOR B with A. All right, we'll update our binary numbers, and so now B has become 25, which is the original value of A. If you look at the combination here, A has become like the same number, but now B has been mutated to kind of be like the inverse of A. But it's that original number that we started with. So now, if we take A a second time and bitwise OR it by passing B sort of through it, watch what happens to A. A becomes 15. And so if you look at what happens to binary A and binary B, you can see that they get swapped to their previous original values. And so because these sort of transactions in this order are kind of the inverse function of each other, this operation is really common in computer science, and being able to pick out this type of operation is useful, but these binary math tricks they're kind of relegated to one area of computer science, which is the really like embedded systems, low level stuff. If you're just doing web development, like you don't usually end up doing a whole lot of bitwise operations. But if you want to do something really, really deep and cool, you're gonna get into the binary numbers. Okay, so that's kind of the basics of swapping two values. Do we have any questions? By show of hands, who's done these like bitwise operations before for some class? Who's solved problems with bit manipulation? Bit manipulation in the past. All right, we got Victor Rodriguez representing the bits. Okay, we got one. Okay. So that's pretty typical. Again, not that many people end up working in this particular set of problems. I went and I actually asked Twitter and I said, hey, ever actually get asked these questions in an interview? And one guy said, yeah, I have, and he worked on the Xbox. So like, you know, he worked on an Xbox and Sonos and HoloLens. So those are kind of the situations where he was working on things that required you to understand the instruction sets for a machine, right? But in, you know, a lot of situations, you're not really digging down into the instruction sets of a machine. So you're not likely to get, if an interviewer is not wanting you to just come up with bit manipulation out of your brain. So I'm just going to show you the solution rather than like arriving at it. So this is kind of how it works. Let's go to the first step. You can see here this here is bitwise OR. I added those binary A steps here so that we could kind of watch it execute, but these are sort of not part of the solution. And so the whole solution is A equals 0 for I and nums, A bitwise OR every number, each one of these elements. And then at the end, you just print A, and you have the number that's left over. Okay, so let's look at this. This is our list. We should come up with 1. 1 is the only singleton. We have a 4 and a 2 and a 3 and a 2 and a 4 and a 2. So none of these numbers are next to each other. It's just that, you know, so long as the bitwise OR is getting the number and then getting the number again, it like adds that number into the sort of value and then like removes it. And so you'll see this happen. Okay, so A starts at 0, and this is what that looks like in binary. We're gonna bitwise OR A against I, and so now A is 4. So you'll notice, basically there's a number of different numbers that you can kind of bitwise OR other numbers against, and you'll just get that same number back out. 0 is 1. And so binary I is 4, so that's kind of what 4 looks like in binary. And you can see that A is now 4 in binary. Okay, and then so you can watch A become 5, and so you watch, you know, that change. But now Yeah, you watch it become 7. And then it becomes 4 again because we ran into, let's see, we added a 3. So yeah, we didn't run into a duplicate yet. Now we're at, A is 4. And then we run into a 2, A is now 6. We didn't really add 2. This isn't an adding operation. But you'll see that at the end, after we've passed all the numbers through this bit, so through this bitwise OR, you'll see A become 1. And that happened like right at the end there. Let's see if I can go back to where A became 1. So at this point, A is 2. It's not one of these elements. It's just the accumulation of all of those transactions having been done and then undone. And done and then undone. And so then it becomes 1, and that's our number. That's the end. So if I didn't have these binary I and A and binary A here things, we wouldn't really be using an extra variable. We would just take the input array, and then we would just have one spot to hold the output value. And this doesn't create a second set. And you can see there's only one for loop. And so we're not doing any like secret loops underneath. We're not like looping over the number and turning every part of it into binary. There's no weird things going on there. And so this is also a linear solution. Bitwise operations are also way faster than a lot of standard operations. Doing things like comparing 2 strings, you're actually sort of writing a double for loop there. Doing things like comparing 2 lists, or even a lot of different kinds of comparison, like comparing 2 data types that aren't the same. It's actually more complicated. There's a little bit of overhead there that you might not realize is there, but these bitwise operations, they're fast because they're built into your processor. Your instruction set already knows how to run them. So that's why this is a lot faster than these other solutions. This is kind of what LeetCode wants you to get to, but really what, to kind of go back to the presentation that I had. Make sure it's in here somewhere. To kind of go back to the presentation. Let's see. I lost my presentation. No. Is it like up here somewhere? All right. It's probably here. Oh, here it is. Boom. There we go. So what you can see here is that it's very similar to the different interviews are going to be asking for different things, right? If you're trying to get to the point where you're in like a bit manipulation interview, you're probably interviewing for like a low-level embedded systems role, not like an internship at like a company that does web development. So don't try to focus on when you're doing internships. Or when you're preparing for internship interviews. Try to focus on the area that you want to go into for this next job or this next role. If you want to get into VR and graphics programming, cool. Definitely check your bit manipulation skills. And I've added some resources in the Canvas that will help you to do that. But, those 3 solutions are 3 totally different categories of approach, right? Understanding all the stuff about integers and like what happens when you multiply sequences to try to get individual things, that's more like signal processing or like, doing some data science, right? The kind of solution there is really dependent on, that you end up coming up with is really dependent on what you're going into. Yeah, there's a lot of kind of different areas that just depend on different sets of skills, and they don't expect everybody to just know all of this stuff all of the time. So just because you got to the math solution and not to the bitwise solution, like that doesn't mean that that you're deeper. It just means you knew bitwise operations better than you understood what happens to, you know, sequences of integers. So I hope that helps. Any questions on that implementation before we disappear? Okay. So the last thing that I wanted to do before we do just a practice exercise together, let's see, is to get over to Replit. And I just wanted to show you list comprehensions real fast and set comprehensions, because if you're reading code and you haven't recognized a list comprehension yet, it can be really hairy. So normally when you see a list, normal list, you see something like this, and there's like 1, 2, 3, 4, 5, 6, 7, 8, okay? So sometimes, though, you'll see a list like this, you know, double list, right? Some operation that you want to do. And then you'll see something like this, x for x in normal list. And what you're seeing here is kind of like a for loop inside of a list. This is really just because going over a list is such, and like doing something to each individual element to it that's small and predictable is such a common thing in Python that they just have like a syntax built in for it. So if I wanted to say, you know, x times 2 for x in normal list, this expression gets evaluated for every element. And every element that's placed in the list is this expression. And when you have 4x in normal list, it's sort of like a normal for loop, right? So if you see, x basically gets declared, and it only exists here, right? So if we run this, maybe we should use Python too. I'll just go ahead and print doubled list. So if you look at doubled list, it's the list doubled. So this is one line of code that can be like a hidden loop that you might not realize is a loop, but it's definitely a loop when you see it. So it's the length of the loop is dependent on another sequence. I can put anything here. I can put like range, you know, 0 to, or like 5 to 125 and step by 5. And then if I look at that, then I have like the 5s doubled stepped by 5s. So I can put whatever I want here as long as this is an iterable sequence. Now the reason I didn't say list instead of iterable sequence is because there's more than one type of iterable sequence. We already saw one. So a, you know, pool set, which is if you use the curly braces and you just say 1, 2, 3. What I'll do is print a pool set. And then if we look at it, you'll see that it kind of prints out. You'll note I didn't put like colons or equal signs or anything in here. So I haven't set these like keys to any values. And so that's kind of what distinguishes it from a dictionary or a hash map from another language. But you can also do a set comprehension, another pool set. And you can say, you know, x or x in double. And I could do x divided by, you know, 5, right, for x in double list, and just see if I get any duplicated results. So you don't get any duplicated results because it's a set. But you can see here that these are the elements of another pool set over here. So again, this first part of it, that's the expression that you're going to transform x, you know, you can like stir, you can turn it into a string instead of dividing by 5. And each one is now a string. And you can see that they're not ordered. Again, sets, not ordered. Like 140, then 90, then 70, then 50, and like zeros in the middle. How does that make any sense, right? So there's no idea of order that's like really super stable. So you can't use a set in a sequence where the order matters. So that's kind of the main difference between these two. And this, you know, if you've seen that like loop all in one line, that's how you write one of these things. Sometimes people will write these really awful, like entire programs that are in like recursive, you know, set comprehensions. So I could have like a set of sets that's like, or a list of lists that's like, you know, X for X in range, or in, let's say, double list. But really what I want is, you know, X times 2 for X in doubled list, and X, you know, to the power of 2 for this already multiplied by 2, right? Oh, and then I didn't print, let's print just this expression here. So you can see, you know, what I've done with these numbers here is I like did a, you know, I've got two sort of expressions here. I like do something here with doubled list, which generates a list inside of another list comprehension. Isn't that super hard to read? It is, it's super hard to read. Don't do this, especially not at an interview. You'll be sad you did, because it's very hard to keep that whole thing straight. Just take this out, put it in its own variable, and then put that variable there, because it's really easy to get confused in these situations. Okay, just been talking for like an hour and a half, so let's pause. Any questions on any of this syntax or any of these concepts? Again, I can dig in, but yeah. I'll also be releasing a video that's similar to this whole thing, so where I'll dig in a little bit more. So don't worry if you know you maybe want to see another run through of this. Also, I'll be posting the video too. Really, no questions? Because after this, what we're gonna do is practice our group interview prep skills. Okay, so what we're gonna do is, so I've seen that y'all are not in groups right now, so I'm gonna try to include a few more group exercises in these. And we're just gonna get used to the idea of kind of as groups in Zoom talking and going into breakout rooms so that you can practice some of the things that you can't practice alone. You can practice code alone. You can rewatch this video alone, you know, in the dead of night and no one can bother you. But what you can't do is always get time with another person who can, you know, be another person who's like really, as another person, evaluating what you're saying and can tell you real feedback as to whether or not that makes sense, right? So that's the scarce thing here for us all gathering together at the same time. So we're going to do a group exercise today where we're going to just talk a little bit about our personal narrative for our career pitch. We're going to practice the tell me about yourself question. You get into an interview and the interviewer goes, okay, so yeah, let's get started. First, why don't you tell me a little bit about yourself? This question is really scary for a lot of people. It seems like a trap. What are you supposed to talk about? It's a trap. It's not a trap. Really, what you're supposed to do is sort of signal things that you find exciting that are similar to kind of the role that you're working on. So if you're interviewing in Microsoft and you want to work on the Xbox, maybe you're really interested in the level embedded systems programming, and I have an Arduino and I've gotten into these other things. That's the kind of response you want to get. Maybe you want to get a job at optimizing. And so you're like, yeah, I've really been reading a lot about distributed systems books lately and like I've really been interested in like how we can optimize, what you're really trying to do is say, hey, I fit in at this group, right? That might mean that you have to like do a little tiny bit of research about what the job is before you have 2 to 3 sentences really to say about yourself. So I want you to just pick a company, just any company, let's count to 10, and then just pick the first company that comes to mind that you might want to work at as a software engineer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you picked one. Even if you want to change your answer, don't change it. You're just going to interview there just to practice, okay? Now, think about what does that company do and what is the job that I'm interviewing for? Pick any area that you might have ever considered once in the past. Don't overthink it. We're going to count to 10 again. Pick something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, picked a company and a job. It's an imaginary company and a job. What we're going to do is we're just going to jump into breakout rooms, and we're going to go for 3 minutes each, and we're going to talk about how basically our whole career has been building up to this job. But try to do it in a way that is like, it's really about you. You don't have to lie and say, I'm interested in something that you're not interested in. Try to think about things in your past that you've done that are somewhat in any way similar to this new thing that you're thinking about interviewing for. And if you can't, think of things that are tangentially related. Either that or just talk about things you're really enthusiastic about learning and what your hobbies are. With hobbies, try to pick hobbies that are sort of related, even tangentially, with computer science. Like knitting is somewhat related to computer science. Cooking requires the management of a bunch of different simultaneous processes. So like those things can count. Just think about how can you tie this thing that I want to sort of project as part of me to I want to be an awesome CS grad who gets this job, and my whole career has been building to this job. It's like an elevator pitch. So we're going to do that. What I'm going to do is click this button and hold on. Hold on. Where is the breakout rooms button? Breakout rooms. There we go. Okay. Continue. I'm gonna go 4 rooms. It's gonna be random, so whoever you end up with, that's your interviewer panel. I want you to go one by one, and I'm gonna stop in each room and check to see that you're doing it. Okay. I'm gonna click this button, and then a thing is gonna appear, and you're gonna say join breakout room. Open all rooms. Let's see, everybody join those breakout rooms. Join them. Only got one person there. Okay. All right. Alex Lewis, Ashley Jacobs, Jonathan Q, Timothy Pham. All right. Y'all should join your rooms. Okay. All right. I'm going to jump into those other rooms and assume that the other 2. I'm just going to move you to breakout room 4. Oops. I was muted. What's up? How'd it go? Did everyone get a chance to chat?
Yeah, we did. We all took turns answering the questions. It was good. It was good. I think it was a good exercise. I think they all got some practice and um, got to hear each other's answers and learn from that also.
Good, good. Awesome. Okay, so it looks like everyone's back together. If you didn't get a chance to talk, or if you want to do it a couple more times, what I recommend doing is literally just make a video with your phone of yourself, like you're talking to someone else over FaceTime. Because, just like talk to yourself, introduce yourself, like you're applying for a particular job. If you do this before every interview, you will nail this question super hard. So any of these questions where you have to be a human and talk and not solve problems, but like just sort of talk it out, you just do it in front of your phone and make a video that you then watch afterwards. I guarantee you'll dial it in to where you're really happy with that answer. And then you'll come in and you'll sound really confident and you'll feel good. So I really recommend making some videos of yourself talking about yourself. It's cringeworthy. It's very hard, and you'll be like, this is terrible. Do it with bad lighting so you can't see your face. But spend some time doing that. You really will get some good practice. And you kind of see how hard that question is. It seems like a simple question, but it really isn't that simple of a question. Okay, so I'm just gonna share my desktop. Are you doing it? No, it's not doing it. Oh no, it is. Can y'all see my desktop? Yeah. Sorry for making everyone dizzy. Okay, yeah, we practice that. So now, yeah, that's the end. Next time we're going to talk about string manipulation. String manipulation is not just list manipulation with characters. Whole different ballgame. So we'll talk over some of the weird patterns that come up with string manipulation and more problem overviews and things like that. We'll also have another one of these like practice sessions where you're going to be asked to talk over a couple of theoretical problems rather than actually coding. So you get a little bit of experience with that. But again, you need like another person to watch you in order to get some really good authentic practice. All right, thanks for coming. And if y'all have any other questions, I'm here for the next little bit to answer those questions. Otherwise, y'all can bounce.
Thanks, Liz. I'm going to take off.
Thanks, it's on. Cool. Anybody want to talk over anything? See ya. Have a good one.